Alright, so question 5 is about magnets and electromagnets. So let's have a look. Diagram 2 shows the positions of the compass needles when the current is in the wire, right? So diagram 1, there's no current in the wire, alright? So what you can see is that all the compass needles are aligned with the Earth's magnetic field, alright? When we've got a current in the wire, okay, then all of the compass needles have aligned themselves to the magnetic field around the wire, okay, and you can see that they're all pointing from north to south, from north to south, from north to south, so they're all pointing in this direction here, okay. Just like these compass needles are pointing in the direction of this magnetic field here, right? So they've aligned themselves with the magnetic field. Okay, so explain why the compass needles turn when the current is switched on. It's because when there's a current in a wire, okay, then that means that there is going to be a magnetic field around the wire, and then the compasses have aligned themselves to that new magnetic field. Okay, and some of you said because it's, because the magnetic field is stronger than the Earth's magnetic field, which is a great answer. Okay, so they align themselves to the strongest magnetic field, which is the new magnetic field created by the wire. Using evidence from the compass needles in diagram 2, draw on diagram 2 the shape and direction of the magnetic field. Well, we've already done it. It's concentric circles, okay, and if you want it to be really fancy, okay, then the circles get increasingly more spaced out as you move away from the wire. Why is that? Because that shows that the field is getting weaker as we move away from the wire. Look, so you can see that the field lines here, they're getting more and more spaced out as we move away from the wire. Okay, and it's clockwise. Why? Because they've aligned themselves with the magnetic field, which goes from north to south. Deduce the direction of the current in the wire in diagram 2. So to be able to do that, we need to use the right hand grip rule. And here's the right hand grip rule out of your textbook. It's on page 201. And you can see that if you align your thumb with the current, then your fingers are going to point in the direction of the field. So let's try that out on this one here. If I take my right hand and align my fingers so that they're pointing around clockwise, then my thumb is pointing into the page, okay? And the way that we signify that something's going into the page is by drawing an X, okay, and then here we say that it's travelling into the page. Okay, next question, we're changing gears now, right? So this was all about the field around a wire, okay, and now we're looking at the motor effect. So we're looking at what happens when we put that wire into a permanent magnetic field. So the permanent magnetic field is from north to south, that's in that direction there. Okay, and the magnetic field around the wire is going to interact with that permanent magnetic field, and we're going to get the motor effect, so the wire is going to move. To be able to work out what direction the wire is going to move in, we're going to need Fleming's left-hand rule. Okay, and there it is on page 208 of your textbook, right? So the first finger's the field, right? Yeah, first finger's field. Second finger's current. And the thumb gives us the motion, right? The thumb gives us the motion. So back to the question paper. All right, you've got to align your first finger with the blue line on my diagram, okay? And then the only thing that you're allowed to do then, okay, is to rotate your hand, right? Okay, you've got to keep your first finger pointing in the same direction all the time. So I'm going to rotate around my first finger until I've got my second finger aligned with the red arrow on my diagram there. And hopefully that means that your thumb for movement okay, is oriented vertically upwards. And if it is, that gets you 2 marks. Okay, you can see that the 3 fingers in Fleming's left-hand rule, 3 digits in Fleming's left-hand rule, they're orthogonal to each other. That means that they're all mutually perpendicular. There's 90 degrees between each of those, right? Okay, so you can narrow it down pretty quickly. It's either going to be going up or it's going to be going down, and then you use Fleming's left-hand rule to help you work out that it's going to be going up. Okay, the power supply in diagram 3 is now replaced by an ammeter. Okay, so we've got rid of the power supply and we've put an ammeter in there now. Alright, so now what are we looking at? Alright, we're not looking at the motor effect anymore. Okay, we're actually moved on to the next topic, alright, which isn't C anymore. We're looking at P6D, which is electromagnetic induction, right? Okay, let's just have a look at the textbook for this bit. Where is it? Here we go. Okay, so this is exactly what's going on here, right? Okay, so as we move the wire through that field, okay, you can see here we're moving this vertically upwards or vertically downwards. You can imagine that wire kind of cutting through those magnetic field lines, all right? And that's the thing that induces a voltage, right? So how do we get a current? So we're going to explain which direction, right? And as you just saw from the diagram, you can either move it vertically upwards or vertically downwards, okay? And it's this idea that this wire here, this red wire here, is going to cut through those blue field lines as it moves either up or as it moves down, right? Okay, so if you've got those 2 concepts, either up or down and cutting of field lines, okay, then that's going to get you the 2 marks there. So explain why cutting any current is produced in the wire when the wire is moved in the magnetic field, right? Okay, key bits explain again, right? So when the wire moves, okay, let's just sketch it out. So there was our field line. Okay, I'm going to draw the wire in red. All right, and I've got lots of these field lines like this. Okay, so now if my wire moves vertically upwards, okay, it's going to cut through those field lines, and what's that going to do? It's going to induce an EMF, an electromotive force across this wire, right? So maybe this end of the wire gets 1 volt and this end of the wire gets 0 volts. Okay. Now at the moment that EMF isn't going to do anything. Okay. Why? Because it's not yet connected to an external circuit, right? So for that EMF to move some electrons, then we've got to connect it to an external circuit. And now, because we've got a complete circuit, those electrons, which are the current, can now move through that ammeter and complete the circuit. So they really wanted something quite specific here, right? They wanted the idea of the cutting of the field lines to induce a voltage or induce an electromotive force across the wire from this end of the wire here to this end of the wire here. And then because we've got a complete circuit, then that voltage means that electrons are going to move, and that's what a current is, right? Okay. So talking about a moving wire cutting magnetic field lines induces a voltage, and then because it's a complete circuit, this allows a current to flow. So quite challenging to get full marks on that question.